Time is a river that never reverses. We are carried along its current, birth to death, sunrise to dusk, cause to effect, never sideways, always forward. And yet the laws of physics, the ones that govern particles, motion, and energy, don't care about direction. Their equations work the same in reverse. They describe a universe where the past and the future are mathematical mirrors. So why, in our experience, is time not a loop, but a slope? Why do we remember yesterday, but not tomorrow? Why does a cup shatter, but never reassemble? Why does a candle burn down, but never rise from its own smoke? The answer is entropy. Not a force, not a substance, but a tendency. A direction embedded not in particles, but in probabilities. Entropy is the measure of disorder, of options, of how spread out things can be. And the second law of thermodynamics tells us something profound. In any closed system, entropy never decreases. Disorder grows, order fades, heat spreads. The arrow of time points one way. But here's the twist. Entropy isn't just about decay, it's about becoming. Stars ignite because clouds of gas collapse in heat. Galaxies form from gravity's dance across billions of chaotic motions. Life itself, structured, self-replicating, complex, emerges not in spite of entropy, but because of it. Entropy is the reason your brain can hold a memory. It's the reason there was a past. The reason there will be a future. It is the silent clock of the cosmos, ticking not with gears but with imbalance. In this episode, we'll explore how entropy shapes the flow of time, how it powers creation, even as it foretells destruction, and how this quiet law governs not just the fate of stars, but the cracks in our coffee cups, the warmth in our breath, and the way we tell stories, with beginnings, middles, and ends. Because time is not just a measure, it is a direction, a consequence. A one-way unfolding written into the fabric of the universe. And entropy holds the pen. Entropy. A word whispered in physics textbooks and shouted in climate reports. A word so misunderstood that it's often used as a synonym for chaos or decay or doom. But entropy is not chaos, it is clarity. It's not the end of order, it's the reason order exists at all, if only briefly. The term comes from the Greek entrop, in transformation. It was coined in the 1860s by Rudolf Clausius, a German physicist searching for a way to describe something invisible, yet unavoidable. The gradual degradation of energy in any system. He needed a word for what was lost, not in substance, but in usefulness. A measure of how energy spreads, how it evens out, how it becomes inevitably less available to do anything interesting. That measure was entropy, and with it came a law. Not a law written in stone, but in heat. To understand why entropy matters, we must go back, not to stars or atoms, but to steam. In the 19th century, steam powered the world. Trains, ships, factories. The Industrial Revolution was built on the idea that you could heat water, make it boil, and turn expansion into motion. But a question haunted the great minds of the time. How efficient can a steam engine ever be? Why, even with the best design, does some energy always get lost? Why do engines get hot? Why do they leak work? A French engineer named Sodi Carnot began to ask these questions in the 1820s. He imagined an ideal engine, one that could extract the maximum possible work from a cycle of heating and cooling. No friction, no leaks. Perfect isolation. The engine was a thought experiment, a dream of perfection. And yet, even this ideal engine had limits. Carnot found that you could never convert all the heat into work. Not even close. Some of it must always go to waste, dispersed into the surroundings, never to be reclaimed. This wasn't a failure of engineering, it was a law of nature. Later, Rudolf Clausius formalized this observation. He wrote, "The energy of the universe is constant. The entropy of the universe tends to a maximum. Energy doesn't vanish, it transforms, it spreads, it becomes less concentrated, less useful. That is entropy." And this principle would become known as the second law of thermodynamics. Where the first law told us that energy is conserved, the second law told us that energy has direction. It can move from hot to cold. It can power a machine, but it cannot stay organized forever. Even in a perfectly sealed system, No leaks, no noise. The energy inside will settle into a dull, useless soup. A state of balance. A state of maximum entropy. Entropy didn't come into physics as a thunderclap. It crept in, subtle, statistical, and quietly final. After Carnot and Clausius laid the foundations, the second law took its place not as a curiosity, but as a commandment. In any closed system, entropy never decreases. It always increases. Or, at best, stays the same. This isn't just a tendency, it's a rule of irreversible fate. You can compress gas into a canister, you can boil water into vapor, but you cannot unpop popcorn. You cannot unburn a match. You cannot unmix milk from coffee. Energy flows. It disperses. The second law ensures that once it spreads, it never reconcentrates. At least, not without help from outside. This is why machines wear down. Why stars exhaust their fuel. Why the universe isn't filled with tight, orderly bundles of energy but with sprawling clouds of it, gradually cooling. The second law doesn't just govern heat. It governs change. And it does something else, to something strange. It gives time a direction. Most equations in physics are time-symmetric. Run them forward or backward, and they still make sense. But the second law is different. It only runs one way. Entropy increases. Eggs crack, bodies age, and memories form. And we know deeply, intuitively, that these processes never go in reverse. This is the arrow of time, not drawn by clocks, but by conditions. It's not that time moves forward, it's that entropy does. By now, you've heard the phrase. Entropy is disorder. It's a useful metaphor, but a dangerously incomplete one. Entropy isn't messiness, it's possibility. Let's imagine a deck of cards. If the deck is sorted as to king, perfectly aligned, there's only one way it can look. But if it's shuffled, there are quintillions of possible arrangements, each one disordered. Each one more probable. Entropy is not just about how something looks, it's about how many ways it could be. Physicists call these options microstates. It's the hidden arrangements of particles beneath what we observe. What we call the state of a system, ice and water, gas in a room, is just a snapshot of many microstates. When entropy increases, it means the number of possible microstates increases. It's not destruction. It's diffusion. Think of an ice cube in warm water. At first it's distinct, structured. Its molecules are locked in a rigid lattice. But as it melts, the water becomes uniform. The molecules spread out. Energy evens. To the eye, the system looks less interesting. But to the universe, it's more likely. More options. More possible microstates, more entropy. And this is the heart of it. Entropy doesn't say what will happen. It says what tends to happen. It says that the most probable future is the one with the most ways of being. And once we started thinking this way, everything changed. Because someone came along to put that probability into math. In the late 1800s, a brilliant Austrian physicist named Ludwig Boltzmann asked a simple, devastating question. What if thermodynamics, this grand law of heat and energy, wasn't a mystical truth, but a matter of statistics? He imagined the world not as solids and fluids, but as trillions of atoms in constant chaotic motion. And he made a leap no one else had dared to take. Entropy, he proposed, is not about heat. It's about how many microscopic ways a system can be arranged, and still look the same from the outside. More ways equals more entropy. He even wrote it as an equation later, carved on his tombstone. S equals K log W, where S is entropy, K is Boltzmann's constant, W is the number of microstates, the number of hidden quantum arrangements that make up a visible state. Entropy wasn't disorder. It was math. It was probability. It was the logic of the likely. And suddenly, the second law wasn't just empirical. It was inevitable. The story doesn't stop with physics. No. In the 1940s, a young mathematician named Claude Shannon realized that entropy had a twin in an entirely different field. Information theory. When you send a message across a wire, through radio, or between neurons, you face a question. How unpredictable is the content? If you know what someone will say before they say it, there's no surprise, no new information. But if every word carries uncertainty, there's entropy. Shannon defined information entropy as a measure of surprise. The more possible messages, the higher the entropy. Suddenly, entropy was everywhere. In language, in communication, in biology, where DNA stores low-entropy blueprints inside high-entropy cells, in computers, where bits flip in ordered cascades to tame entropy into function. Entropy became the bridge between physics and knowledge, between heat and thought. By now, you may wonder, is entropy just a concept? Just a tool? No. Entropy is more than a number. It is a law of direction. It tells us not just what is possible, what is probable. It governs the tendency of systems to evolve toward more likely states. Not by force, but by math. It applies to everything. From steam in a cylinder, galaxies forming from cosmic gas, to the aging of your own body, entropy doesn't just describe change, it drives it. It whispers, gently but insistently, that everything flows outward. That heat will spread, that clarity will blur, that order will fade. But in that fading, something else begins.